Alright, so in this problem we need to find a polynomial of degree 3 with real coefficients that has zeros at -4 and 1 plus 3i, and we want f of 0 to be 8. So one form of degree 3 polynomial is we could have something like we want f of x equals, and then we need real coefficients, so all of these could be 3, and it's degree 3, and in our most generic form we have all of this. Now we also know that we can leave it in factored form, and we actually have some factors. So when we're talking about kind of our generic factored form, we have our function. Now one thing that we know is that our factors, we're going to have 3 of them, right? It's degree 3. So we have x, and then we have some constant, and we have another one, and we have another one. Okay, so those are our factors. And then the thing to keep in mind is, notice here we had this coefficient out front. If we multiplied these through, we just have x cubed, and we wouldn't have, we'd have an a value of 1. So we need to have something out here that's our stretch factor that we have in here. Now, what some people did was thought, okay, we know from our green form here that if I put in 0 for my x from here, that I get 0, 0, 0, and then I just have my plus d, which would be my 8. That's true in that form. However, we can't just put a plus d on the end of this, because then our parts in parentheses are not actually zeros. Because if we put in, say, -4, and we get this would not be 0 anymore, because as we multiplied it out, we'd have the plus 8 at the end. So we wouldn't actually have a 0. So we need to keep that in mind. The other clue that we have is that we know that we have real coefficients. Okay? And we can see here that our 1 plus 3i, that's a complex 0. So if I had that in one of these spots, then I wouldn't have real coefficients when I multiply that out. The only way to get rid of that is to multiply by the conjugate. The conjugate is the thing that you multiply such that your imaginary part disappears. So that's what we have to find. And the part that we do for that is we need to find the thing that we can multiply this by to get rid of it. So if we look at a 1 plus 3i, and we want to get rid of the imaginary part, well, when we're multiplying binomials, most of the time we notice that if we have a difference of squares, then we don't have a center term. And that's what we do here. If we have this minus in front of the imaginary part, then when we multiply through, we get our 1s, we get a positive 3i, and then we get a negative 3i, and that's the canceling part. And then we have our plus 3i and our minus 3i, which makes negative 9i squared. Now, for some reason, a lot of students decided to put negative 3i squared there, but you have 3i times negative 3i, so you're going to get negative 3i squared. And so we can see that these two cancel. So we have 1 minus that, and you might think, well, we still have an imaginary part. But we know that I squared is equal to -1, so it's rotated back into the realm of the real numbers. So we have actually -1 times -9, so +9, so 1 plus 9, and that gives us 10. Okay. So then that tells us we have our 3 values. we know we have our f of x. We don't have our a yet, but we need to keep it there. So we have x minus our 0, which is -4. So minus a -4. I'm going to go ahead and write that out for now. Keep that in mind as we move through these. And in the same way here, we have x minus our next 0. Our next 0 is 1 plus 3i. So we need to make sure that when we write these out, that we have our x minus and then the 0. And then as we found, our other 0 is the conjugate, so minus 3i. And so each factor should have this x minus form, and you can simplify those a bit. Now the next thing to note is that we want to have, when we input 0, f of 0, well, we want f of 0 to equal 8. But that also tells us that we can put in 0. So I have a 0 plus 4, 0 minus 1 minus 3i, 0 minus 1 plus 3i. And we can simplify a bit now. So I have a times 4 times -1 minus 3i, -1 plus 3i, and then of course this is 8. Now, one thing that we notice here is that this looks very similar to what we've already done here. We just need to check with these minuses what happens. So if I have a -1 and a -1, I still get the 1 out front. Taking a -1 times a positive 3i, I get a -3i, which I had, but in the reverse spot. If I take a -3i times a -1, I get a positive. So I still get the positive and negative version, which should be clear because these are still conjugates. And then my -3i and positive 3i is what I had earlier, which came out to a positive 9. So I'm still going to get this value of 10. So I'm just going to write that as 40a equals 8. So a must equal 8/40ths or 1/5. Okay. So now as I rewrite this in my final version, I know that f of x equals 1/5, that's my a, and then since I can leave it in factored form, I'm just going to have x, I'm going to go ahead and make that plus. You could leave it minus minus, but it's simple enough. And then x minus these, I'm going to go ahead and leave undistributed to make it clear what the zeros are. And then other common mistakes that I notice is for some reason people wouldn't put the second parenthesis there. Some people forgot to put the x minus part and just put the root there or the 0. All of those things are just kind of maybe not paying attention, not being clear enough, but we should be able to finish with something that looks like that. One other thing that I noticed is some people, instead of doing the conjugate here, thought that putting a minus in one and a plus in the other would accomplish that. The problem is that's not a true conjugate because you'd get a -1 and a positive 1, and that's not what we want. We don't care about adjusting the real part of the complex. We want to eliminate the imaginary part. And the reason we know that we have that conjugate is because we have real coefficients. And so as we multiply this out, if we moved it into our green form here, our a, b, c, and d would all be real values. So maybe I can go ahead and do that real quick. I'll do that in a follow-up video.